All right, so we're going to talk about now inverses, or basically the opposite of the conjugate of matrices and what the properties hold in their form. Well, before we get there, we'll just do a simple example of linear equations. So given the form of 4x equals 8, well, we could solve for x by just dividing both sides by 4, right? That's pretty much, we know what to do that. Well, the problem is we can't really do that when it comes to matrices. That's a bit of a big no-no. In fact, we can't even divide matrices, okay? So what we're going to do is just go back to here. And now that we know a little bit more math, let's just do the opposite. So remember, here we'll just divide by a to both sides, or it's technically multiplying by 1 over a to both sides. Okay. Now, going back again to a little bit of exponents, we can rewrite 1 over a as a to the negative 1 power, right? So theoretically, right, technically, you're just doing the long way around of this simple example is, well, I could solve for x, where a and b are arbitrary, by multiplying by a inverse, or 4 to the negative 1 power. Just like that. Okay? Which means these go away, and we find that x is equal to this. Okay? Now this is how we do matrices. Because we can't divide with matrices at all, we have to do something called the inverse. So we're going to first find the inverse of a matrix and then multiply by b, and that's how an alternative is solving for the x variables themselves. Okay? So in other words, if we go now to an actual, break this down into matrix format, well, we have ax equals b, then solving for x just gives us this. Exact same format as if it was just a general number itself. Okay? So now let's actually give the definition of how to find it, or what is an actual inverse of a matrix. So let matrix A be an n by n matrix, and we'll say A is invertible, and you could find an inverse, if we could find an n by n matrix, a to the power of negative 1, or inverse, such that this is actually true. Okay. So when I do matrix multiplication on the left or on the right, you still get the identity matrix, and that's the key thing. Okay. If that's true, then therefore this is called the inverse of A. Okay. So, new definition, let's try this out going forward. So given the n by n matrix A, show that A has no inverse. Okay. All right, so this is an arbitrary one, right? So we're going to follow this process. So we're going to say that B, B1, B2, B3, and B4. Okay. And I'm just going to multiply them, because I'm going to assume this is the inverse and get the identity matrix back, sorry. Okay. So let's actually do that. All right, so just straight multiplication, see what we get. So remember, it's going to be this row by this column. Okay. And now the same thing. And here. Okay. Now remember, this is supposed to be equal to the identity matrix. So what that means is B1 plus 3B3 must equal 1. And so does this one. And the others must equal 0. Okay, so what if I just divide this by 2? I get that. And notice I have this and this. It's kind of a contradiction. And in fact, we get multiple contradictions because if I do the same thing over here, we get this back. So there's no possible way where this sum both equals 1 and 0 at the same time. So hence, not possible. So in other words, A has no inverse at all. Pretty interesting way of doing it, right? Now, the next couple of lemmas and theorems intertwine what we already know to what an inverse represents. So the first lemma, let P, Q, and R be n by n matrices, such that the multiplication of P, Q gives you R. If either P or Q is singular, then so is R, and that's a key thing. Okay. And now it goes to our theorem, which becomes a non-singular. Let A be an n by n matrix, so always a square. Then A has an inverse if and only if it is non-singular. Meaning now we have multiple stuff happening, right? Linear independency means non-singular, also means you could find an inverse, meaning it's invertible. So now we have 3 extra things applied just to non-singular linear independency. Okay. All right, so the question now becomes, how do we actually find an inverse? So to find an inverse is pretty straightforward. We're still solving for the variable, right? Nothing's really changed. So the only difference is the fundamental fact is we're going to eventually flip it around like a mirror image. So we're going to follow this format, and we're going to eventually get to the point where this side gets reverted to this side. And then this matrix over here would be a inverse. So basically you're just solving for the variable, like, just make this the identity matrix and just revamp it, and you eventually see that this is the A inverse itself. Pretty interesting stuff, right? So just a little longer process. We have much more numbers everywhere, right? So just take your time to do so. So we're going to go from the hard one, 3 by 3. So we want to find the inverse of a 3 by 3 matrix. So first thing, we're just going to rewrite this down. And now I'm going to write my identity matrix. Okay. And now again, at this point, I'm just solving, right? So I want the identity matrix to go over here. So we just follow the same template we've been doing so far. So let's see. Multiply this by -1. Add it to the bottom one. Okay. There we go. All right, so I'm actually do the same thing, just multiply by -2 this time. And put it to the middle. And there we go. All right, so a third of the way done. We got one down, so just 2 more, just rinse and repeat 2 more times. Okay, so I'll use the middle one, I guess. So multiply by -2. Good. All right, so far so good. So this time I'll multiply this middle one by 3. Actually, I'll just do it down here. Okay. Looks like we're pretty much done. We got this and this down. So this one can pretty much help the rest of it down. All right, so a little bit more work. You just do one more step. So I'll multiply this by -2. Ooh, multiply by 2. Sorry, so this is 1 these times. Okay, there you go. -16, 7, and 2. There we go. Right. And then finally, just do one more time. Multiply this by -7 to get rid of this. And eventually, we get our inverse. And there we go. So this would be our inverse matrix right here. So a lot of lengthy process to get there. But it's still about the same thing. Basically still solving for variables in a different way of doing it. Okay. All right, next couple terms. So let A again be a square matrix. Then A is non-singular if and only if A is row equivalent to I. Which what we prove here, right? Which makes sense. It's a consequence of that. Right? So we can find we can find if it's invertible, if it's possible to convert it to the identity matrix, right? Using row reduction. So, interesting example here. Given a system of equations, so just two systems. Find the inverse of the coefficient matrix. Solve for the system x equals a inverse b. Okay. So let's do the first one. It's only 2 by 2, so it shouldn't take too much to go by. All right, so multiply this by -2. And multiply this by -2 and add it together, and we have our answer. So our A inverse will be the matrix 5, -2, -2, 1. Okay. Now, for part B, when we want to solve for this type of portion, all we're going to do is multiply A inverse by our B. Well, actually, I think I have a space in the back to do some graduating. So X will equal our inverse times B, which is just the answers themselves, right? So in this case, it's going to be -1 and -10. And it works, right? This is a 2 by 2, and this is a 2 by 1. So the result is going to be a 2 by 1 matrix. Okay. So row by column. So this means x1 is 15 and x2 is -8. So an alternative to do so, there's multiple ways now to solve for systems now with this introduction to inverses of matrices. Okay. Now, you may think that's a lot of work to find the inverse, and going forward, and yes, it is. It is a lot of work. However, we do have a nice equation, or formula if you want to call it, for 2 by 2 matrices. Unfortunately, it's only for a 2 by 2 matrix. So given any arbitrary 2 by 2 matrix, as long as A times D minus C times B doesn't equal 0, we could find the inverse. However, if the subtraction of this multiplication gives you 0, then you have no inverse. But if you give me anything but 0, negative number or any number is possible, decimals or fractions, we can find an inverse. And the inverse of this matrix A, again, only for a 2 by 2, would be this. It's 1 over literally this subtraction times the matrix, and you're just going to swap these around and just pop a negative in front of these. And that's guaranteed to work, ironically enough. Again, only works for a 2 by 2 matrix, unfortunately. So now let's try this out instead of having to do the whole, going to the row echelon forms and all that fun stuff. So let's see if these two exist, and if they exist, let's actually find it. All right, so if you follow this format, it's going to be this minus that times that. So 6 times 6 is 36. 3 times 12 is also 36, which gives you 0, which means no inverse. Why? Well, if it equals 0, we have no inverse at all. Now let's try the B one. So this is for matrix A. So for matrix B, so 1 times 5 is 5, minus 3 times 7 is 21. So that difference is 16. So this is a yes. It is non-negative, so we can find this inverse. And the inverse is going to be 1 over negative 16. You flip A and D, so in this case it's going to be 5 and 1 here. And these stay the same, just opposite sign now. And there is our inverse. So much nicer than have to do all the work. But unfortunately, like I said, this only works for a 2 by 2 matrix, so shortcut. Okay, so now we can do a little bit more theoretical approach. For what values of A is a matrix A non-singular? Find the inverse if A is non-singular. Okay, so we just talked about this, right? It's a 2 by 2 matrix, so we'll do the same process we did earlier. So in other words, to make this non-singular means it has to be linearly independent, or the subtraction of this multiplication has to be non-zero. That's exactly what we do. So multiplying, so it'll be A times A minus 3 minus 2 times 2 is 4. Okay. So let's just set this equal to 0 just for now, so we can see what's going to happen. Okay. So we're just going to solve for A in this case. So distributing, okay, and just simply solving, right? So factoring or quadratic formula, but I'm pretty sure we need to do quadratic formula for this one. Positive 1 and negative 4 looks like. Yeah. So A equals 1 and a equals -4. Okay. Now, these are the values, or actually, I guess opposite, right? -4 and +4. Looks like you almost solved them. So these are the values that make this singular. So to make this non-singular is all real numbers except when a equals -1, yeah, -1, and a equals 4. Or you can put all real numbers, not including those, right? Those are, so I can pick any other numbers except those that make this non-singular. Okay, so that works. Now we got to find the inverse of a, which is, we already have it here. So again, if it's not these numbers, then we actually can find it, which means we can find or get the inverse itself, or in other words, the general inverse of this matrix. So same process, you flip these around, and just pop a negative in front of those two. And there's our inverse. All right, so now goes to one of our major theorems based off inverses and their properties. So let A and B be n by n matrices, each with its own respective inverse. Then all these four are true. A inverse has an inverse, and the inverse of an inverse is equal to its original A. If AB has an inverse, then the inverse of AB, you can actually flip it around. So you it's basically the distributive property for inverses, but instead of straight, you have to flip these around first, just like kind of like a transpose as well. If K is a non-zero scalar, then Kx has an inverse, where you could just, same process, comes into play. And the last one is transposes with inverses. A transpose has inverse, and that inverse represents this process here. Okay, so we're going to try to prove the first and the second one. All right, so like everything else, we're going to follow a process. So the A, B, n by n matrix with an inverse. Okay. All right. And in fact, we're going to do a little bit more. We're going to let A to n have an inverse. Where A is the inverse. With. Okay, so because this is the inverse of this part, think it backwards, by the property, we know this is true. Okay, by definition, I have an inverse. All right, so now what we're going to do is we're going to do the inverse of this side. Now, according to property 2, because of this, therefore, it's basically the distributive property flipped around. So now I'm going to have A inverse times A inverse to the inverse there. Okay, all right. On this side, the middle part is just I by this definition. Okay. Now I'm going to multiply, well, let's just start from here. The inverse of the identity matrix is itself. Okay, so now what I'm going to do is I'm going to multiply both sides by A, like this. And it's going to do it on the left side. Well, this ends up just being I, again, from over here. This side, A, the identity times any matrix is just itself the matrix. Well, again, the identity times any matrix is going to be itself. And look, we get that. Check. It works. Okay. So now let's try B. Or sorry, not B, second one. So now I'm going to prove the property we just used here. Okay. So we'll again follow this process. So we're given since has as an inverse. So A times B has an inverse. Okay. I'm going to let A, B inverse be it. Okay. So therefore, this is true. Just like we did up here. Okay. Okay, so now we're going to split up into two different parts. Okay. We're going to show it actually has an inverse, and then from there, show it is the only inverse. So what that means is we're going to show that this is the actual inverse, not just that. Okay, and it's a unique one, meaning they're the same thing, right? Which is basically what we're trying to prove here. Okay, so we're going to show two different ways, right? By the property of an inverse, we're going to show the left and right equal I. So we'll break it down to step 1 and step 2. So first we're going to show it is right multiplication. So we want to show that this side gives me the identity, which means it's an inverse or exactly that to begin with, right? It's a unique one by definition of an inverse. Okay, so according to our properties of multiplication, right, I can now write it like this. Okay. Now, the cool thing is, by this theorem, we know that A and B are individual matrices who also have inverses. Okay? So that means this is just going to give you I. And the same thing, I times any matrix is going to be itself. And again, like I said earlier, A and B have inverses. So this is also I. So check, it does actually work. So it works on the right-hand side. So all we have to do now is show the left-hand side also applies. And you can tell it's going to be a basic mimicry of what we just did. Again, because they're inverses of each other, it doesn't matter if you multiply the left and right. This is still going to give you I. And there we go. So in fact, is the inverse of AB. But so is this. By the definition of inverses, they are unique. Well, if they're unique, therefore they're the same. Because you can have being unique two different ways. There we go. So we're actually going to be trying to disprove number 2 right now with this example. If you're wondering why do we have to move them around instead of having just a straight distributed property, again, just like transpositions of matrices. So let's do this example. Given matrix A and B, show that the left doesn't equal the right. Okay, so again, we'll just split it up. We'll do this part first and then do the other part, given these two matrices. So first we got to multiply A and B together. So row by column, and then row by column, and then another row by column, gives us this. Oops. And now I'll do the inverse of this. All right, so is this by this minus that by that? So negative 7 minus a negative 18. That's 18 becomes positive, so it becomes just 11. Flip these around, change the sign, and there's our left side. So now we're going to do the right side. And then for the right side, we have to do each matrix inverse individually, then multiplying. So A inverse is going to be this times this minus that times that. So 1 over 3 minus a negative 8. Oh, sorry, no, over here. My mistake. Oh, no, that's right. It's A first. So 3 times a negative 8. So that's going to give you 11. Flip these around. And then B inverse. 3 times 1 is 3, minus 2. So it's just going to give you 1. And then finally multiplying these matrices together in this format. So I'll keep the 1 over 11 on the outside. And again, row by column, row by column, row by column. And if I do my math correctly, we should get this. And as you can tell, they are not the same. So we prove it doesn't work. And the last thing in this section is these major theorems here. So let A be an n by A matrix. And the best part is all of these are equivalent. So it's a nice little checklist when it comes to every single thing we've done so far. So if A is non-singular, therefore it's linear independent. Therefore there's a unique solution. Therefore we can find an inverse. And therefore it's row equivalent to I. And again, vice versa. If one of these is true, all of the rest is true. So it's a nice little checklist for these 5 major things that all apply and give you the same exact thing. So if you could show that one exists, that means by default the rest are also the same and true.